All right, welcome back for some more fun with math. We are in the midst of the chapter on limit cycles and how to detect or rule them out. For the last couple videos, we've been looking at different methods for ruling them out. And now we're going to start tackling the question of when we can show that they have to exist. And this is the essence of the Poincaré-Bendixson theorem. So, to give a little bit of motivation for how this is going to work, we're going to play very much with the topology of the fact that we are sitting in two dimensions, and that is going to severely restrict the limiting behavior of what our solutions can do in autonomous systems. So let's motivate it with the following example. You might recognize from last time that the system here looks very, very close to the example that we did last time, so it means I should probably indicate that, okay, this system has the unit circle for its limit cycle, but the one that I was using as my example at the end here from last video, this one would actually have the radius 2 circle as its limit cycle. So, correction now made. Don't at me. Okay, so coming to this example, we can see that there is this blue shaded region, right? It looks kind of like an eyeball, right? A really irritated eyeball. But the blue region here, I'm going to go ahead and call R, right? And this is, for all intents and purposes, a topological annulus, right? So R here is what's known in the trade as an annulus, and this is actually the Latin word for a ring. All right. So anyway, we'll get back to annuli in a moment, but this annulus has two boundary components to it. It has an outer boundary component C1 and an inner boundary component C2. And what we'd like to do is track what the vector field is doing across both of these boundaries, right? So you'll notice on the outer boundary, on C1, that x dot here is always pointing at least a little bit in toward the interior. It's pointing toward the R region. Right? So that's what I'm highlighting over here. That these kinds of vectors, if I'm looking along C1, are pointing toward the blue region. Okay? And you'll notice something very similar happening with the inner boundary. That trajectories are pointing out away from the origin, but again, toward the blue region. So these guys want to be pushing initial conditions so that they stay inside of this annulus that I'm calling R, this blue region. So, and that's the whole takeaway, is that once a trajectory enters this little ring region, that it can't leave, right? There's no way, right? If it tries to approach the boundary here, the vector field is going to direct it back toward the blue region to stay inside. And the fact is that we've kind of fenced off the boundary and said, you're going to have to stay in here once you enter. So this is what we call a trapping region. For some reason, I changed the letters here. That makes no sense. These are all R's. Interior R, R, enters R, region R. R is therefore called a trapping region, right? Once we have established that we have a trapping region for some system, and we know that the solutions can't be attracted to any other points within that region, then we get the Poincaré-Bendixson theorem. Okay, now this guy has a couple of different statements. Here's the first version. Okay, so let's go ahead and give ourselves our autonomous system, and this is specifically, again, for a planar system, right? This theorem is actually not valid in dimensions higher than 2. We'll see why when we start talking about chaos. But let's say that we're dealing with a C1 vector field, so it's continuous with continuous first partial derivatives, and R is going to be some compact trapping region. So this is going to look like an annulus. Okay? And this annulus R is going to be such that F, the vector field F dotted with the unit and outward normal is negative, right? And that condition right there might be a little tricky to digest. Let me just remind you, this dot product is just asking how much of F points in the direction of the unit vector, okay? And that is at every location. So this isn't an integral of f dot n hat. No. This is just a straight up evaluation of a function on a pair of circles. We're asking, does the unit normal point with the vector field F, or can we definitely make sure that this guy is actually pointing away from F at all locations on that circle? And sure enough, right, that works for both sides, right? So that'll be an n hat here and a little f right here. Sure. The dot product there, right, we can see that the angle between these guys is greater than 90 degrees. So the dot product is surely negative in this case. So that just means that f and n are pointing in inherently opposite directions. Oops. Let's see if I can zoom in and kill that term. Nah, so close. We can do it. Yay, there it goes. And we fit the page width. Yay. Okay. And we can do the same thing down here and ask, remember the unit normal now is going to be pointing outward, right? So outward away from D. So that means that this guy actually flips directions on us as we go to different boundary components, and the inner versus the outer boundary. So again, the red vector is pointing away from the black vector, so the dot product between the two is negative. So coming back to the statement of the theorem, that's all we're asking in here, is that we are guaranteeing that this is an honest-to-goodness trapping region where the vector field is pointing in toward R at all points on the boundary, right? Both boundary components, the inner and the outer circles. And statement number 2 here is just to guarantee that there is nothing else for trajectories to be attracted to within that region. So this is ruling out the problem of maybe there's a fixed point that lives right here that a solution could conceivably be attracted to, or from maybe later on down the line. We're just making sure that we know all of the different ending behaviors that could occur within that annulus. So if we satisfy conditions 1 and 2, we have a trapping region that has no fixed points in it, then R has to contain a limit cycle for the system. Right? And that actually should make a fair bit of sense here intuitively, that the trapping region is making sure that once you enter the annulus, you never leave, and that once you're inside this annulus, there's nothing for you to be attracted to. So the only thing that's left for you to be able to do is kind of cycle around and just wander aimlessly, so to speak. But because we're in the plane, we can't wander aimlessly, right? This is actually going to be a consequence of uniqueness of solutions combined with the Jordan curve theorem, saying that every closed curve has an inside and an outside. So there's a very limited number of possibilities for what this limiting behavior needs to look like, or what it can look like. So once we've established 1 and 2, we've ruled out every other possibility, and we're left with a limit cycle. At least one. And the proof goes like, no, I'm just kidding. We're not going to prove this one. It's fairly complicated and requires a good bit of differential topology in order to prove rigorously or convincingly. So think about it geometrically for the time being, and that's perfectly acceptable. So let me give you an example of how this works. So the example at the top of the page satisfies the condition of the theorem, right? If I scroll back up, I have a trapping region, and I don't have any other fixed points in the system apart from the origin, and the origin is not within the trapping region, so we're clear. So the Poincaré-Bendixson theorem does apply. There has to be a limit cycle, and we see it. It's the unit circle. Right? In order to show condition 1 rigorously, I mean, we can go ahead and use our numerical simulation just to give us an idea that we might be able to find a trapping region. To actually show this rigorously, I've gone through a computation here of how you might actually see what the unit normal vectors look like on the inner and outer boundaries. Right, these are your standard radial vector fields, unit radial vector fields. And you just compute the dot product explicitly. So you're just taking this dot product of what your vector field looks like against some outward pointing normal vector. Right, and you get a plus or a minus depending on which boundary curve you're sitting on. So remember, C1 is out here and C2 is in the interior, or it's the inner component. So if you go through this computation, which I recommend you do, right, verify what I do. Don't just take it on blind faith here. It's a bad idea. Or at least it's better for you to understand when you do something for yourself than just to listen to somebody talk about it. So notice that we wind up down here where we can do this in terms of polar coordinates, right, the polar radius. So we wind up with f dot n being equal to this in general. And more importantly, it's negative on both C1 and C2, right? In fact, it's a constant on both of those, strangely enough. In general, f dot n hat is going to be a function, but we luck out that I chose a system where this is actually a constant function. So, might happen to different degrees depending on where you measure, but notice that I'm choosing very particular C1s and C2s, right? So C1 and C2 are defined where on the outer radius I have a root 2, is that right? Okay, I might have actually done that for a 4. So I'm doing this for r equals 2 and r equals 1/2 for C1 and C2. So the algebra might not be quite right, but it still holds. Okay, and if I do that carefully, yeah, that's what I did. This was for, oh, I did do it right. So this should be a 4 instead of a 2. There we go. Now the math works. Right, so the algebra is all fine now. But let's see. Therefore, f dot n hat here, right, the vector field dotted with the outward pointing normal vector is negative everywhere on the boundary. Therefore, all trajectories that pass through boundary R can never exit back through boundary R. They have to stay within R. Okay, so that's just how you might verify the trapping condition explicitly. Okay, not too bad, I don't think. And that was really nice that we had a very, very simple geometry that we could invoke. In general, that's not going to be quite so nice. But let's see how this looks in practice. When we come across a model and we have to figure out what's going on exactly, where we might be able to see limit cycles. Now, Strogatz actually goes through an entire section here talking about glycolysis, and I really like this example. It's extraordinarily simple, right? It's overly simple from a biological standpoint, from a biochemistry standpoint. But this is one step that has to be done through the gigantic chain of events that we call glycolysis, where we take glucose and turn it into energy, or ATP. Right, and ADP is one of the precursors, one of the necessary molecules that we're going to have to use to create an ATP, an adenosine triphosphate molecule. So what we would like to do here is show that this chemical reaction is actually modeled by this system, or that there is a simple way to think about this in terms of the law of mass action. So take it on faith right now that this is the non-dimensional version, or the non-dimensional form, of the first, or one of the first few steps in glycolysis. And in fact, this should be the first step in glycolysis, if memory serves. So we're going to use X to measure ADP, and Y to measure fructose 6-phosphate. Phosphate, my notes say. That is a phosphate. There's the H. Hello, H. Okay. Knew you were in there. Okay, so this is one step in going from glucose to ATP and pyruvic acid, or at least the pyruvate ion, or polyatomic ion. And A and B from this system of equations are both going to be positive constants, and these are going to represent kinetic rates. So they're telling us how quickly these reactions occur. So the B here is actually going to represent a feed rate because we're sitting inside of a chemostat. It's effectively telling us how much sugar we're adding to the system, how much of our reagent we're adding to the system and allowing to be broken down. And we're just saying that happens at a constant rate, B, or that we're creating fructose 6-phosphate at a constant rate, or we're arranging for that to be the case. Our goal now is to show that there is a stable limit cycle within this system. Right? Usually glycolysis and most chemical reactions want to be asymptotically stable toward a stoichiometric ratio, that we eventually get to a nice equilibrium in how much of the concentrations of each of these components eventually winds up, or how much of each component we should see in a long time reaction. Or there's once we realize that once we're in chemical equilibrium, we should be in stoichiometric balance, is what this is saying, or what I'm saying. So we would like to show that there is a simple mechanism by which we can still establish glycolysis. That glycolysis can actually continue without an asymptotic stability in the ratios between ADP and fructose 6-phosphate. So let's do it. Let's show this. Well, we're gonna operate as per usual, and we're gonna compute some fixed points. So we're gonna go ahead and set our vector fields to 0, and we'll pick up our null-clines in that way. Right. So this first equation, this guy right up here, is going to be our vertical null-cline, because we're killing off the x dot component, and the exclamation point down here. Oh, come on. Our exclamation points. This is going to be our our horizontal null-cline, right? So we've computed null-clines, and we can do a little bit of algebra to show that if we were to find any fixed points here, we have to set these two guys equal to each other. That means that x and b have to be identical, right? There's but the one condition that we can satisfy here to make this true. So these two curves intersect only at the non-trivial equilibrium here. And that's actually exactly what we expect, right? So chemical reactions typically are asymptotically stable in the long term, right? They want to go to some stoichiometric ratio. And that's exactly what we see in that fixed point, that there is a stoichiometric limit. But we try linearizing the system here. We're going to try to see what this looks like nearby. How are we approaching that limit? Is it a node where everything sucks in pretty quickly in an exponential fashion? Or does it oscillate in some way? Well, not too bad. Let's have a quick look. So if we were to linearize this guy, you can compute your first derivatives, right? Going back to this guy here, right? So this would be the f and g functions of the f and g components of the vector field. And we see, oh, come on, don't auto. There we go. Yeah, the light started, my backlight started going, sorry. Let's see. So the linearization for our limit here, for our fixed point, right? So our fixed point is going to be linearized with the following determinant. And I make the remark that this is a positive number, which means that it's not a saddle. Damn, I was hoping we didn't have to do much work. Oh well, that means that we have to go ahead and compute the trace of the of the Jacobian matrix, which we now know better as the divergence of the vector field. And we're going to compute that divergence at a very specific location. We're going to do this at the fixed point, right? We're going to do this up here. So the trace is actually easier to compute than the determinant. Or actually, in this case, the trace is actually a little bit trickier to compute than the determinant. Go figure. Fractions are hard. Okay, so a little bit of long division in this last step is going to show you that this is what we get for the trace. And unfortunately, the trace could be positive or negative in this case, and it depends on the balance between the two constants a and b. Right, we've seen this sort of behavior before, where we have to define kind of this boundary curve of different relations between the parameters that force different kinds of behaviors in the system. So in particular, I can show you that the trace is negative if I take that particular pairing, and the trace is positive if I take this other one. So there's got to be some dividing line where the trace is equal to 0 that separates these two cases, where I can actually show that this is not a node but actually a spiral for certain cases. And actually, we're going to go ahead and jump straight to the numerical simulation in here. Feel free to follow along with p-plane for these particular parameter values. That it turns out that this is a stable spiral, right? The non-trivial equilibrium, or the only equilibrium, I suppose, is a stable spiral, and we spiral in the clockwise direction. But if I choose a parameter regime for which the trace is positive, then the stability of that spiral actually reverses. But I still have this global, like, sucking in behavior. That stuff far away from the origin wants to come back in and cycle toward the equilibrium point, the fixed point. But the fixed point itself wants to throw things away from it, right? The divergence is positive. So that means that there's something happening in between. And since there aren't any other fixed points in this system, Poincaré-Bendixson is going to show up. So we're going to have to come up with a trapping region for this limit cycle. I have to figure out how to trap that guy with respect to the vector field. And Strogatz actually proposes the following region. A lot of the time, you can go ahead and follow coordinate axes, straight lines, circles, right? It's very simple geometric objects to define the boundary of your trapping region. Okay, so the textbook is going to say that we have this little pentagon here, right? It is a pentagon. It doesn't quite look like it, but it's five-sided. So this region is going to be kind of the foundation for where we're going to place our trapping region. Okay, so the dashed lines here are going to be the outer boundary of the trapping region, C1 from before. It's got 5 different components to it, A, B, C, D, and E. And for your sake, I'm going to go ahead and show you what it looks like on A and B, and then leave you to figure out what C, D, and E look like. But on the left side, right, we're going to go ahead and say that this is occurring on the y-axis, so that means that x is equal to 0, and y is going to be stuck between 0 and b over a. Right, and we know for a fact here that the outward pointing normal vector is going to be this horizontal vector pointing to the left. So this is the negative I hat, right? So this is negative 1 by 0. And we compute directly f dot n hat is just going to be a times y. Did I do that correctly? There should be a negative in here. Yep, that's right. So a negative ay. Yep. So the negative ay, both a and y are negative for just about every point on this region, right? The only place where it's not is when y is equal to 0, and that's acceptable. It is a set of measure 0 on the boundary with respect to the one-dimensional, or it's a set of measure 0 inside the boundary. So the boundary is already a set of measure 0, but if I think about the boundary as being a new space, and I think about a single point on there, that guy is going to have measure 0 within the topological circle boundary. But anyway, so f dot n hat is going to be negative on the A branch. A similar argument is going to show that f dot b is going to be negative on the B branch. And that one has zero problem whatsoever. Okay. So this guy is also negative. So we've gotten 40% of the way to a trapping region. Right? We've gotten 4 or 2 out of the 5 boundary components, and shown that these guys are definitely influxing. So I leave it to you at home to show that C, D, and E are also going to be influxing. Right? The picture shows that that might be the case, but I'd leave it to you to show this more rigorously. So I think the hardest part is figuring out what is the normal vector on this slanted region, right? C and E are easy enough to figure out. You've got J and I respectively. But what does it look like on the boundary here? This looks a little bit tricky, a little bit different. So I'll leave you to think about it. We can certainly discuss it in class if you'd like. But to finish constructing the trapping region, we need this to look like an annulus, right? So right now, this is a topological disk, right? It is a solid plate surrounded by a topological circle. So this guy is definitely not a trapping region yet because we haven't established the annulus. And a quick way that we can do that is to punch out a disk from the interior of this region R. Okay, so we would like to punch out something where we know that divergence is going to be toward the region R. And a great candidate for this is the one and only fixed point that lives inside this region, which if we satisfy certain conditions on the inner boundary, specifically with A and B parameters, that the trace of this, of the Jacobian here, right, the divergence of the vector field is going to be positive in a neighborhood of that fixed point. So we are going to require that to be the case. So we're going to go ahead and go back up to our condition up here on linearization to say that this trace needs to be positive. Okay, and that, if you do this algebraically, okay, there we go, is going to be this condition in the box. Oh. We need to make sure that we satisfy this condition, which is the same as down here. And this is exactly what they do in Strogatz. And it turns out that these are the parameters that you can use that will give you a limit cycle versus what will give you a stable spiral. Okay, so it's entirely possible now for us to say that under certain conditions in A and B that we can use Poincaré-Bendixson to guarantee a stable limit cycle for this system. All right? And the reflection I'll just go ahead and say is this, that glycolysis can proceed in an atypical fashion to chemistry, where chemistry usually wants to move toward an asymptotically stable stoichiometric ratio. But glycolysis here, under the right kinetic parameters, can actually go into a cyclic behavior, right? We can kind of trade off between ADP and F6P and oscillate between varying concentrations of the two to continue glycolysis with seemingly no ill effect, right? But it looks like ADP, because it's a precursor to ATP, yeah, you're going to wind up in certain parts of that cycle, specifically, let me see if I can find it again. In specific parts of the cycle, remember X is going to denote the ADP, but in certain parts of the cycle, you're going to be sitting on a very low output of energy until your F6P can join the party and then start bumping X back out. Right? And we're going to continue along that cycle thusly. So it's it could be considered ideal or non-ideal depending on your interpretation of when you get or when you would like there to be oscillatory behavior in your chemistry. But the fact is that glycolysis can proceed in a cyclic fashion, not necessarily in this limiting asymptotic stoichiometric ratio. Number 2, trapping regions can be rather difficult to identify and verify. So it's actually not a bad idea to be sitting there with your computer and running simulations to figure out or give yourself an idea of what these limit cycles look like so that you can better understand how to construct a trapping region, right? It's not cheating here, right? You're trying to figure out, when do I have a limit cycle? And I think it's totally within reason to bring the computer into play. Right? This is not trivial in general. So third is that limit cycles can spawn out of fixed points. Much in the same fashion that we have kind of guard points around a central equilibrium in a pitchfork bifurcation, we can change the stability of an existing fixed point so as to produce another fixed point in the system that has that stability. And this is exactly what we see. We change from the stable fixed point to an unstable fixed point, and as a result, we can actually spawn a limit cycle from that location. This is not the only way that we can get limit cycles to occur, but it is definitely a nice prototype, and this is essentially how the Hopf bifurcation works. So congratulations, you have now seen a practical example of a supercritical Hopf bifurcation, or a limit cycle spawning. We will come back to that in Chapter 8, but for right now, that's about all I want to say in 7.3 about the Poincaré-Bendixson theorem. There's one more thing, two more things that I'd like to say from Chapter 7 here, but we'll go ahead and roll them into two different videos moving forward. Right? It should be a fairly brief conversation, but at the very least, I think this is one of the most powerful theorems that we have in 2 dimensions. Right? This is going to give us a characterization of what we can, and more importantly, what we cannot do in planar systems. And we'll talk about that in the next video.